Okay, so we should all see a little red dot in the upper left-hand section of our Zoom windows, and that indicates we're recording. So with that, I will hand over the session to Mr. Sean Martin, who is going to describe to us his experience with setting technology readiness levels in his work with the U.S. Department of Defense.
Good afternoon, everybody. I'm happy to be here. First, I got to put a little caveat, since this is being recorded, that my views and my opinions do not reflect that of the U.S. government nor of that of the U.S. Special Operations Command. I'm providing you my experience over 33 plus years of different technology projects and readiness and so forth, and maybe some lessons learned, if you would. So my current position is I'm the Deputy Program Manager for Soft Lethality, Special Operations Forces Lethality. And in your left-hand side of this slide, there's a warfighter holding a small arms at M4A1 with a close-in optics sight with lasers and lights and so forth. That's what my office does. The ammunition for that weapon, the sights, as well as additional precision guided missile systems. That's what we're responsible for. We have a budget about $200 million a year for a portion of special operation forces, Green Berets, Rangers, SEALs, SWICs, combat controllers with the Air Force, as well as Marine Corps Raiders. So with that, a little bit about myself. A bit about me. I once upon a time attended University of Florida, graduated with a mechanical engineering degree in 1986. This is a time when the mechanical and aerospace programs were separate, and not sure exactly when they integrated, but it was a basic ME degree. I got my master's degree from the Naval War College 20 years later, and which is not necessarily a complementary degree for the engineering, but for my line of work with Department of Defense, it's turned out to be quite useful. So while I was at UF, I participated in the American Society Mechanical Engineering Students section, both as a program chair and vice president. And when I graduated in more of the professional ranks in Bay County, Panama City, where I used to live, as the program chair, vice chair, and chairman. And I share that with you because those are easy and good opportunities for you, one, to network, but two, build some of your leadership skills, which you may not have the opportunity to do it elsewhere. And they were beneficial to me, building some leadership skills. And I just offer that up as a, an idea for you all. My employment, first job out of school was as facilities engineer in Southern Bell in Panama City, and I put that there because I was there for about 14 months and absolutely despised the job. And some people love it. It wasn't for me, and I offer that up because some of you in your first position out of school may not like it. That's okay. You just have to understand. You have to know yourself, what things trigger you, your interests, your passions, and so forth, and find the right fit for you. And I did. So I left the phone company Southern Bell, and I went to work for the Navy at the Naval Surface Warfare Center, Panama City, as an engineer, where I designed a variety of undersea systems or enabling systems like the flyaway recompression chamber for Navy EOD. I designed a submersible outboard engine that I got a patent on, and a variety of other systems. After 10 years in Panama City, I went down to U.S. Special Operations Command in Tampa, the MacDill Air Force Base, as as an engineer in their Science and Technology Directorate, which I stayed for most of my career down here. I've been down here for about 24 years now. And that acronym soup behind SOCOM is a variety of different positions, not all that important in our discussion, but the reason why I put down there, just let you know, I just didn't sit in one position the whole time. I'm continuously learning and growing and taking on different responsibilities. All right, technology readiness level. Dr. Traum asked me to come and chat with you all about it. And it's not really an academic course per se. It's really something in the the practical application of engineering, the business or the government is used a lot to understand the maturity of technology. And so we'll talk about that, some definitions, why it's important. And I've got about 4 case studies of my own and some of the things that bit me and what I learned. And by the way, we don't have to wait until the very end for questions. Please feel free to ask any time along the way. In fact, it will actually be good because it'll help me think of different things that I may skip, okay? So technology readiness level was conceived in NASA in about 1974 for the Jupiter orbital spacecraft. And the reason for that is NASA had been plagued for some time with a non-common understanding of the maturity of subcomponents. And some of the subcomponents were being integrated into spacecraft and they weren't ready, but they had no means or a lexicon or measures to determine they weren't ready. So they established TRL as a mechanism to help with that. And so common definitions, common understanding, it helps you to quantify risk for critical components. And what I mean by critical components is those components, if they fail, it's loss of mission or loss of life. So for example, in your car, if your interior door handle breaks on your new car or even an old car, that's not a critical failure. But if your engine blows up, yeah, it's a critical failure. Or worse yet, you have a blowout on a tire and the car rolls over and kills you, even a worse problem. So it's those components that are really critical to the function or the safety of the device. Make sense? Okay. So one of the things that you closely look at with safety and defining and identifying those critical components, there's a variety of ways, but they're all very similar. One is the failure mode, failure modes, affects criticality analysis, FAMICA. Sometimes the criticality is not in the label. We use, as it's shown over there within the Department of Defense, what we call a safety standard, but it's a standard practice for safety, and it's MIL standard 882 Echo. And we use that religiously, absolutely, in everything. For example, the weapon systems that my office fields, every one of them go through a safety analysis by expert weapon engineers with the Navy. And they determine what the risk assessment is for each. And depending on the risk, low, medium, or high, there's different signature authorities accepting that risk. Typically, though, if it's high, nobody's going to accept it, and they're going to tell you to make some corrections. But in doing a criticality analysis, if you will, it helps you. You also have to think about the probability of failure and the criticality of the nature of the failure. So how often do you think it will happen, and what happens when it happens? So this is the standard format for that NASA put out for TRL. It's a bit rudimentary, but I think it defines it fairly well. 1 to 9 on the left, level 1 to 9 goes from extremely immature, basic principles observed, all the way down to it's fielded, like you could say a car that you bought off the lot. And every step in between there is things that you have to do in a macro sense to mature the technology. And I'll get more into that as we go. But in some levels, it's subsystem development. But then when you get into subsystem integration into a complete system, that's a whole nother step of integration. Here's a different representation of the same thing, and I included this because it gives you a good understanding where University of Florida research, some of them are all universities, really kind of center on the basic sciences, 1, 2, and 3, TRL 1, 2, and 3. Some observation of basic principles to a proof of concept prototype, somewhere in there. Very low TRL. Quite often, the intellectual property of these things are sometimes licensed out to companies and to companies 4, 5, 6, and 7 TRLs, those are the main areas where I've worked throughout my career. Add a little bit of 3, add a little bit of 8, but more 4, 5, 6, and 7. And that's really kind of taking a basic concept and making some kind of usable prototype that you can demonstrate in an operational environment. So, and there's some differences in what's an operational environment, relevant environment, but we won't split the hair today. Industry typically is level 8 and level 9. And as I've mentioned in previous classes, industry typically doesn't have an engineering department for new technology, not so much. Once upon a time, for example, AT&T had what was known as Bell Labs. Bell Labs was a big technology incubator that fed their industry, but also other industries. For example, they're the ones that developed the fiber optics that we use today for communications and data transfer. But those are very expensive facilities and people to keep employed. So over the last 2, 3, 4 decades, industry has largely cut those R&D sections out of their companies because there's no return on investment, or sometimes there's limited. So the business practices today, big industry, Boeing, Lockheed Martin, so forth, they have some capability, but if they need something that they don't have that's a little bit more immature, they try to buy it. They try to buy a company. And in my business, my time, I've seen this happen over and over and over again, that the big conglomerates buy out smaller businesses so they have the technology. Any questions up to now? Okay, we'll move on. So yeah, that's all nice, lots of words. So why do I care? Why should anybody care, right? Oops, sorry, that was my speaker. So hopefully I'll be able to impress on you why you should care. So with the TRLs and with the system design, you have to make a lot of trade-offs from a system for the complete system. And some of that's performance versus cost, performance versus schedule, safety versus cost, absolutely. And product launch schedule, cost, and company reputation. And so just, I think it was yesterday, Johnson & Johnson was noted in the news that their COVID vaccine caused blood clots in at least 6 people that were identified, and 1 lady passed away. So that was 6 out of 6 million, pretty low percentage wise, but so the product is being pulled back, but I would bet you that their stock prices are going to go down a little bit because the company reputation has been tarnished by that, even though from a probability point of view, the statistics are very, very low. But anyway, so that all goes into play with companies developing things and selling them, or for us, sending them out into to the warfighter. So as I was mentioning here, it's another layer of the same discussion, is some of those pressures can cause you to miss things, absolutely miss safety things that you wouldn't think about necessarily, or you ignore. And I'll give you an example, and I brought up this last class, is the Challenger disaster. I did 2 different case studies on that, and the O-ring on the Morton Thiokol, a solid booster, a rocket booster. It was known to have a certain temperature threshold that you could not go below because it loses its elastomeric properties. But there was tremendous pressure on the president to put the first woman into space because weather had delayed the launch, I think, twice before. So the NASA director gave the go-ahead, we're going to launch, even though it was below the temperature, the minimum temperature, and with disastrous results. So some of the things we do as engineers can be compromised by other decisions, other politics, and so forth. So just bringing that up, this is something that's always in the mix. It's not all pure technology, absolutely not. So there's always compromises, and you have to think about those things. So I'm going to bring you 5 case studies that I personally were involved with, and they're all a little bit different from one another, and just give you an idea about TRLs, trade-offs, and so forth. So this is a project that I started with one other guy in 2010, dry combat submersibles for SOCOM. This is for the Navy SEALs. It's about a 40-foot craft. And so its mission is clandestine insertion and then coming out and releasing swimmers, locking swimmers out. So most of the boat, the majority of the boat was well understood technology, from materials, from the steel in the hull, the pressure hull, to the fiberglass skin, to the control surfaces. Everything was very well understood. What we had, though, based on the performance required of the system, the speed and duration of operations, we had an energy problem. We needed more energy than commercially available systems would provide us. So we had to develop battery systems. And one was built or based on silver zinc battery chemistry, which has been around since about 1960 with the Apollo program. Very well understood behavior, but very low cycle life. You get about 25 cycles out of things until you have to throw them away because they're worn out. But they have a very bad habit of giving off a lot of heat when they're discharging. They're quite exothermic, and to the point that they'll melt the cases of a cell and the cell next to them. So they can have, I won't say catastrophic failure in the sense of deaths, but catastrophic in mission failure. So we were working with, we're developing system. I put several $1 million into this and looking at heat management and how to keep the heat down as they're discharging. And it was a lower TRL. Let me flip down to TRL. So key elements demonstrated in a laboratory environment. So that battery system we were building and testing in a lab. I did not want to put it in the boat because it wasn't mature enough. For initial builders trials, we're using a basic absorbed glass mat, low energy density battery, which we knew was a safe, very, very safe, but we only got about 2 hours of run time. So we were checking all the other systems out, how well they perform, but the battery system we needed was at a TRL 4. Another chemistry effort, lithium ion batteries, which are far more proliferated around the world, and everything in my laptop here, etc. We had an effort underway with that and General Atomics, and using a 18650 format cell. And this was really a battery management scheme that was important because this was umpteen thousand cells in this battery, and also a mitigation scheme in case one cell did start to torch off, they wouldn't propagate to the next cell next to it. So it was a low TRL and very expensive, but the payoff was, as you can see, you have an order of magnitude more cycles. So looking at technologies, looking at the TRLs and the payoffs is just part of what any engineer is going to do, building a system eventually. We looked at fuel cells, and I should have put on the slide and I didn't, is we looked at them. There was 2 different efforts. I went over to Hamburg, Germany, went to Siemens and talked to their fuel cell head of fuel cell production there. And one of the problems we had is logistics, global fuel logistics for it. It wasn't common to the military system. And so we would have had to try to introduce a new fuel, and I think it was methanol. I could be wrong, but I think it was methanol, into the big fuel logistics process, which seemed to be overpowering. But the other aspect of is fuel cells don't have the same shape factor as batteries do. Batteries can pack away in little cells in nice cylindrical shape. Pressure vessels, fuel cells, the fuel cell would have to be completely redesigned to fit in that packaging. So from a TRL, from its current shape, it was TRL 9. Heck, it was been in a German submarine. But for our applications, it would have gone down to TRL 4, just trying to wicker it into a different form factor. Too expensive. I should have put that on the slide. So my point here is one of the critical systems in this boat, and most of it was all very mature technology, some integration challenges certainly, but a very critical component was the power source, the energy source. And so we had three that we're working with, and we had to manage the TRLs, understand the TRLs, and then start making trade-offs. Any questions about this? Okay, somebody should be asking me, which one did we pick?
Which one did you pick?
Oh, I love that question. Lithium ion, because it gave us an order of magnitude more life cycles, but it was also much lower in maintenance, as it says right there. So we could charge the batteries in place. We didn't have to take them out of the tubes. We also didn't have as bad of a heat concern with those. They do heat up a little bit, but not nearly like silver zinc. So, but partly we did that because that's where the industrial base is with power sources. Fuel cells is ubiquitous, and silver zinc cells were something from 60 years ago. They're only limited production up in Connecticut at 2 different places if they're still in business. So we were following industry, what we could tap off and leverage, and also maintenance.
I actually have a follow-up question on the lithium ion batteries.
Sure.
Was that something that you were able to find commercially, or did you have to actually like find someone to make batteries specific to your needs? So I'm working in a battery lab, volunteering in a battery lab right now. So we kind of examine both sides of like what's already available and like what we want to try to make. So
yeah, certainly. So we were using off-the-shelf battery cells, lithium ion, with the format that's called 18650, and it's ubiquitous. Millions are spit out probably every month, from Korea to Japan to United States. I believe Tesla started their own plant up in the United States a handful of years ago, so they wouldn't be beholden to a foreign supplier. But they're all the same little form factor. I have funded battery development efforts, lithium pouch batteries in the past. And the problem is we got the technology right and they were wonderful, but getting them into production to the point that they're affordable is very difficult. And so you have to have a large commercial use or sales to amortize the cost. So in this case, we couldn't. Battelle Ventures bought the little company out. They tried to, actually, it was up in Alachua. It was called Planar Systems, and they tried to go into production there. And they just never could get enough market share to make them affordable. So you're balancing a lot of things. So you're balancing technology, but you also, when you're trying to make a product and buy things like we do, affordability. And so it's kind of market acceptance. So we use cells that are same size as cells that are in laptops and such, but we just use a bunch of them.
okay, awesome. Thank you.
Yeah. So I'll move on and chat about that enough. Here's another little project I had about 5 years ago. I had a little money, a couple $1 million dollars that I was told to investigate what we can do with additive manufacturing to improve capability. And so I had 2 of them, and one was looking at reducing radar cross section of certain type of cans. But the other one I did was this biomimicry for body armor. And this is kind of an interesting one. I worked with Oak Ridge National Lab on this. And the hypothesis was this is the mantis shrimp. And the mantis shrimp feeds by attacking prey. They're the predator. That's got a little fist right here, if you will, like a little ball. And it can thrust and move it supersonically below the surface of water and hit its prey, mollusks, clams, such, and crush the shells and eat the animal inside. But they don't break. They don't break down. And so the hypothesis was, and this is right here, the gray area is well, I don't know if it's electron microscope, but the breakdown of the fibers in the fist itself. And you can see the model next to it in yellow. is a continuous bias ply of the fibers. And so the hypothesis was that when the fist hits its prey, you have a shock wave then propagates through the fist. And things typically break with a shock wave when it hits the back face through what's called impedance mismatch. But with the constant changing of direction of the fibers, our hypothesis was it was redirecting the shock wave radially out, and it never hit the back face. So working with Aerojet Rocketdyne, who builds rocket engines for NASA and the Air Force, I guess maybe even the commercial world, they were spending significant money. They got a significant funding from DARPA, it was about $30-some odd million. And they were trying to reduce the time to manufacture and the cost to manufacture rocket engines by using additive manufacturing, so they would have fewer components. They could build all the functionality into far fewer components with that manufacturing technique. So we were leveraging that money, but also their investigation or research into metallurgy. So what we did, we were looking at stratifying the density of the metal from the strike face and the exterior, which where the projectile or bullet would hit, and then go from maximum density, less dense, and then the center, it would be fairly sparse. And the theory was that we could then change the direction of the shock wave and it wouldn't propagate back to the back face. I don't know that we ever proved it, but I will tell you that this little plate, which is about 5/16 of an inch thick of titanium, withstood a 9mm ball ammo just fine. So interesting science project, but it didn't go anywhere. So from a TRL point of view, I think we concept demonstrated analytically, sure, and experimentally. You could also say in a laboratory environment. So it's TRL 3 or 4, but we never went anywhere because there was a competing armor technology, which is I think it's called ultra heavyweight polymer, or whatever. I forgot the exact term for it, but a polyurethane, ultra heavyweight polyurethane that is being used in manufacturing. They're lighter, much lighter, much more thin specimens and body armor, but extremely expensive to build. So this didn't go anywhere, but it was an interesting exercise. And so from a TRL lessons point of view, is about a 4 we got to it. So this is a project I had some 15, 17 years ago. It was called this surface planing wet submersible. And it's something I was on a design team probably 10 years prior to that, where it's a surface planing craft, as you can see from the photo on the left, but it also has a battery system, a ballast system, a top skin that's foam, closed cell foam cord, and it can become a wet submersible. So you stop the boat, take on water, submerge it down, control its buoyancy, and then you're traveling under the water. As you can see from the photo on the right, those were some of the subsurface propulsors, as well as some of the control surfaces to stabilize the boat. Well, what happened was we had a very mature design of the boat, at least from basic materials and assembly point of view. The hull was aluminum. I think it was 5056 aluminum, marine grade aluminum. We understood how to build it. We understood how to design it. The top skin was, as I said before, foam cord, e-glass, fiberglass, well understood. Some of the work we were doing is the integration of all these disparate parts to a very unique capability. So that put the whole boat fairly at a low TRL. But the subsurface battery system, like the dry combat submersible, was one of our key technologies that it was down here. We were still working on it in the laboratory environment. We were doing heat soaks, cold soaks, vibration, charge, discharge in a lab, very controlled lab environment. And we're having problems with it. And so we sent it back to the prime contractor and said, hey, it's not working again, it's drop capacity. They sent it to their subcontractor. and did the repairs. And instead of sending it back to the government to continue our lab testing, it was given back to the prime vendor who inserted into the craft, which they didn't have permission to do, but it sometimes happens that way, because they had their congresswoman and her entourage that they wanted to take out for a spin. And so my point of mentioning that is just sometimes you have other factors that come into play in decisions. And in this case, it was political connected to the money that was obtained to build this boat. So the vendor was trying to show good faith to his political sponsor, but it cost us, because after that ride on the boat, the next day they're rear charging it, and at the top off the charge, the battery caught fire. They pulled it out of the shop, and they're burned to the ground. And so it's a bit of a lesson learned, but my point, and I mentioned it earlier, is not all decisions when you're developing things come from a purely technical point of view. There are things that compromise what you do. And in this case, the vendor made a mistake, and a bad mistake. And it cost us, because the whole thing went away, if you will. So there's a lot of factors to consider when you're building things and integrating. So overall, the boat was a very high TRL, maybe a 7, but the battery system was a 4. So integrating that low TRL into that boat was too high of a risk. Here's another effort that I spent quite a few years on, and not just the seat, but trying to reduce the injury of our special warfare combatant crewmen and SEALs that ride on combatant craft. I led this effort started it and led it for about 7 years. And this is a little film clip of these seats being used. These are prototype seats. They're not production seats. And the reason why I got the clip in there, I got the president of the company building them in there. And one of the reasons why this is important is I was on this boat one night with these seats, one night off of Biloxi out in the Gulf of Mexico, and riding around, bouncing around, and I could feel something with the control algorithm for the suspension. And this is a semi-active suspension element where it changes orifice size continuously to change the damping characteristics to prevent injury. And I kept feeling something, a behavior that was very uncomfortable, not injurious, but very uncomfortable. And the SEALs and the SWCS we had on hand driving the boat, they didn't pay attention. It was just so much better than what they normally had. So I told the president of the company, Bill, you need to get out and ride it for yourself. You need to, kind of suck it up, get on the boat and understand the dynamic. Let your nose burn when the boat slaps real hard. And so here's a little video clip with the seats. And I will tell you, this is a tremendously nice ride. Oops. Come on, work for me. So that rides like a Cadillac compared to what they're used to. And I've worked with a lot of these guys over the years. And most of them, when they get into their 40s, have their hips replaced, knees replaced, fused vertebrae in their cervical spine. It's just very, very damaging. So my objective was to try to lower the injury to these guys. And so and I think we were fairly successful in doing that. This was one of the efforts. We also built seats for a different craft, the Mark V, that were very successful and fielded. And then we also I worked with Drexel University, University of Virginia, Duke University, Naval Medical Research Institute in San Diego, and a variety of other groups. I pulled together a working group, and we're able to come up with, those smart people, not me, we're able to come up with an injury threshold standard that passed peer review. And that standard has been included in the American Society of Test Methods, ASTM. I think it's 1776, if I'm not mistaken. It was included in that. And with that, we use that to produce our next craft as a requirement the combatant craft medium. And the combatant craft medium now rides wonderfully, because it was the first time as a command we actually took human exposure threshold to repeated mechanical shock as a design requirement. So we put the human as part of the trade space and the design, which had never done before. Naval architects don't do it that way. They use the discomfort of the human to control the pounding to the boat to protect the boat. I took a different approach because I'm not a naval architect, and I thought the humans got to be in the same trade space, and it worked. It worked nicely. Any questions on this? Okay, so one of the things and the point that I'm making here now, this seat looks really mature, production ready. It's pretty good, but we actually had a variety of immature aspects to the seat. So from EMI, electromagnetic interference, the control boxes and actuator for the valve was actually interfering with the radio system, causing static on it. We had some corrosion issues that we had to get after, and we really didn't have enough durability, maintainability, and reliability information to know how long they would last. So while they were pretty good, going to, TRL chart here, I would put those where they're at as a TRL 6, maybe a 7, because while it functioned in a limited test environment, we didn't have it fully vetted out and qualified for continuous use and some of those other things. We got it there, but right there, that rendition you're seeing here was not there. So and I bring this point up is sometimes looks can be misleading, and vendors will try to sell you things saying it's completely ready, and boy, by golly, it looks really nice, looks really mature, but there's so many subsystems that weren't vetted, or should I say fully qualified. So as a good engineer, one of the things you should always be doing is asking questions, asking a lot of questions. And by doing that, not only do you learn, but you also get to the root cause of many things. Any questions on that? I guess it's the post-lunch doldrums, huh?
So that TRL level is basically the like prototyping phase and testing that everything works. How often does stuff usually get there? Is that
what do you mean by getting there?
like because I think earlier you said a lot of them were still in the like laboratory environment, but these are being tested in the real environment, right? They're actual. Right. Does it often reach that level where you can test in the real environment, or do like external, like you said, like the political reasonings come up that cause you to stop earlier? I don't know how. It's kind of a hard question. I'm not really being concise.
No, I think I completely understand. There's a variety of factors. So one of the things we say in science and technology, at least within the military, is that if everything you built in science and technology transitioned to a fielded military system, you're not trying hard enough. You've got to try to push the edge harder, farther for more capability. So the transition rate, I think a very good transition rate from science and technology to a fielded product for the military is about 20%. That's a good fielded. And sometimes because you're trying very new things. And sometimes you do things, and this goes back 20 some odd years. We were one of the early funders, SOCOM, along with DARPA, in Bluetooth. Bluetooth was the name of the company. And when they were a micro little company, we were pouring money into it so we could do connectivity. And we also did a lot of video compression algorithm development because we needed to move videos and photos between operational units and so forth for battlefield intelligence. So we were very early investors in those capabilities, as well as DARPA. Obviously, they have deeper pockets than we do. But sometimes commercial world picks it up. The iPhone adopted many of those same capabilities, with video compression and Bluetooth and on and on and on. So that's good for us when that happens. But again, transition rate, I would say, and somebody could always take exception, but I think if you could do a 20% transition from S&T over, you're doing pretty good. But sometimes the transition will take place 12 years later. You're done, your project's done, and it's 12 years later. And the residual knowledge that was left is then kind of just smoldering and it's picked up by somebody else, and it is then later injected into something, if you will, included into another item. So the traceability sometimes is hard, but once you know a project or the technology, you can kind of do it. But sometimes it takes a long time. You know, the very first photo I showed in my intro slide was the M4A1 carbine, you know, battle rifle that our folks use, a lot of the military use. That started out really as a SOCOM science and technology project many years ago, before I got there, in fact, right before I got there. And it was intended to be a small carbine for our helicopter pilots in case they had to down their aircraft, they would have more than just a sidearm or a pistol. And that started out as a technology demonstrator, and it worked pretty well. And it sat on the shelf for a few years. And then more and more of our units started paying attention to it, and we adopted it. And then in 97 or 98, Big Army decided they really liked that. They went away from the M16 and they adopted the M4A1. But it started as a little science project at SOCOM in like 1995. So sometimes there's great traceability. Sometimes it's a little bit harder to trace it. That makes sense?
Yeah, that makes a lot of sense. You'll like do something and then later on someone will come back to it and don't often know, like it could be a long time.
Yeah, I can tell you the ASTM standard 1776 for the ride quality standard to reduce shock or injury on our boats. Besides me, one other guy at the command who was involved with it with me knows about it, knows its origins. Now you all do, but it doesn't stay. You know, the knowledge, the corporate knowledge, as people come and go and come and go, they don't realize that came with me fighting for money to help reduce the injury of these guys. But that's okay. But there is traceability, but sometimes it's not easy to see.
Yeah, that definitely helps. Thank you.
Sure. So my last case study is, and we talked about some other things in previous lectures, were intended use and being aware of the intended use of things. And so while certain products, certain things may work very well in one environment, one intended use, they may not work well in another intended use. And you have to appreciate or try to understand the differences. And this was a prototype craft from one of our international partner nations that was built by a company that makes, they make a lot of police and pleasure boats, are intended to go fast, but not really operate in the waters and the way special operations boats are used. And so this was being demonstrated over in Europe, and a friend of mine was on it, and the coxswain overdrove it because the water conditions were not appropriate for how he's driving it, and threw my friend out, and it killed him. And so you can see there, they're pulling the boat out of the water, but the ambulance is there and so forth. So my point in bringing this up is that you always have to look at the intended use of what you're designing. And because there's limitations, there are absolutely limitations to what your design is. And so sometimes to mitigate those risks, you know, for a critical failure, you have to change. Sometimes it's your training, sometimes it's your maintenance, sometimes it's maybe reducing the power on the boat. But you have to look, you have to go through failure modes process and analysis, and it doesn't always happen. The boat looked real slick, very mature, but it wasn't quite for the intended use that it was used in, and it was deadly. So main points today is the TRL is the kind of common thread with all this, with risk mitigation, looking at criticality of failures and so forth, is common terms and understanding. And understand you sort of don't get any shortcuts. When you have like those battery systems that are working in a lab or somewhat working in a lab, you have to go through all those steps to prove them, to qualify them, to put them in the operational environment. And when you skip a step, like you saw in the fire on the boat, sometimes catastrophic things can happen. So, but it's a way with TRL and also criticality analysis to help you understand your risk. Is quantifiable to a certain degree, and then manage your risk. And sometimes your risk, you manage it by trading off like those 3 different battery systems and the dry combat submersible. Sometimes it's by putting more money into it. Sometimes it's, excuse me, by stopping the effort because there's too much time and cost to fully develop it, like the biomimicry body armor. So, and all that being said is safety, safety, safety. I can't say enough about that. The burning boat that I showed you, I have that framed in my office as a reminder that you can't stop thinking and asking questions, because we all learn better from our failures than we do our successes. So that's one of my failures that I try to learn from. And with that, questions.
So you showed a few examples of failures related to how you were storing the energy that you were trying to use in your systems. And I think you were saying that a lot of those were like 10, 15 years ago, stuff like that. Like,
Sure.
Has the technology that failed you then, have you seen it improve in that time, or has that been kind of stagnant?
Oh, I think it varies, right? So it's all depends on the commercial marketplace for the most part. And that is companies like Elon Musk or Tesla are pushing using the 1860 cell format, I believe. And they are constantly improving or have constantly improved their battery management system. And so through a variety of techniques, some of it, one technique is you don't charge the batteries all the way to the top. You don't top them off. And I don't know if that's Tesla's way to manage part of it, but that is a technique. So yeah, when there's a commercial application, on and on and on, it's being refined and updated. When there's not as much of a commercial application, who knows? Who knows? How much effort will continue to go into? So with alternative energy, sure, things are going in there. Money keeps going into it. They're improving somewhat, but it's very tough physics. So does that answer your question?
Yeah, I think so.
The commercial marketplace dictates so much, absolutely so much what we can do. You know, we try to put money in and do the really hard things that industry, there's no place for it. For example, the human injury, when I stepped into that so many years ago, there was absolutely zero work done for this dynamic in this situation. There was some ejection seat standard for a single impulse ejection out of fighter aircraft called the DRI standard, but for ours with a repetitive insults, repeated mechanical shock, there was no literature on it. There's no studies. So we had to start very low at like TRL, maybe 1 or 2. And so we had to make some guesses on the seats and then, and also on the data we were collecting and the model we were using. I think we had to interpolate a little bit or extrapolate rather a little bit, but it was good enough. So I say we came up with the 80% solution. So how much more is going into that? I couldn't tell you. I know there's more suspension seats on the marketplace than there was 20 years ago.
Okay. Thank you.
You're welcome.
You might have covered this in some sense, and if you did and I misunderstood, I apologize. But let's say you want to work with an older technology that was given a specific TRL, like let's say it was given like development or demonstration level, and then you come back to it, you find it. Do you need to reevaluate it from the very beginning at its experimental phase to make sure the technology still works, or can you often just take it as it is?
Yeah, great question. It depends on the data that's available. And if there is data to show its use and reliable use and so forth, you got a starting point. If you don't have it, you're at a bit of a risk. So you got a couple of different things at play there, right? One is the TRL of the component itself, and then with the integration, if it's going to be integrated into another system, that is, it is subsystem going into a system, you have to look at that immaturity as well from a power data and connection point of view. That can be relatively minor, the integration risk or TRL, but it's still there. So you have to separate it out. Where's your TRL? Where's your risk? Your boundary conditions, right? Basic design theory, if you will. And so it depends. If you got good data that you can rely on, that, yep, we can start right here for a very similar application, sure. But if your application is very different, I would think twice. You know, I would look for a little bit more information.
I see. So it kind of depends on what you're working with, the system, the conditions, everything. It's not like one yes or no.
Oh, it always is. It's the intended application, right? The intended environment, the intended function, and so forth. The answer is always it depends. And so you have to put all your knowns and unknowns, boundary conditions, all those common things down and just work through it, and then try to understand risk. If this part fails, like going through a FAMICA, what happens? So if a part fails in a small arms development effort, and we have a number of them going on, from too high of chamber pressure, we can have catastrophic failure of the weapon, which could injure, blind, or kill somebody. So we will always, always, always monitor chamber pressures. We will always do certain things to make sure that we are known the weapon is within the safe limitations. But it's something you have to look at. It's case by case basis.
Yeah, I understand. Makes a lot of sense. Thank you.
You're welcome. So any more questions up to now?
Yeah, I had one. Do you know if there was any way of mainly like lower ranking military individuals to contact either, I don't know who they would get in contact with, but like essentially just an engineering group that could look at specific issues that they feel would be unsafe? Because it's usually the lower down guys that are seeing these messed up situations, but they send it up the chain of command and it usually gets squashed. So where they could just like report, and then I don't know, some small team could take a look at it just briefly and then see whether or not there's anything of substance there.
Yeah, that's a real good point. And so there's validity in the lower ranked person finding a problem, but there's also some validity in going through the management chain, if you will, of screening it out. And some of it just depends, and some of it can be money. Some it can be that they already have something moving forward. But we do that a bit. So one of the things I didn't mention is about 5-6 years ago, I was put in charge of establishing our innovation center at SOCOM. It's called SOFWERX, SOFWERX. So I led the small government team to put that into place. And that's located in Tampa, outside of McDill in Ybor City. And that's a place, to get to your question, the heart of your question, where we do, or they do, have allowed that input problem solving from the warfighter back to us, and it doesn't get screened. And that was one of the functions, is trying to keep the filters off and let's take a look at it. Sometimes we spend a little bit of time just in brainstorming, trying to understand it with technical people, operators and such. Sometimes we put a little money into it, or SOFWERX does. So we do have a bit of that. Is it everything we need? Probably not, but it's better than what we used to have.
Okay, I appreciate that. I was
Sure.
just wondering because back in the day when I was in, one of the big issues was the Osprey, and both of everybody knew there was issues with them, but there was no way of getting that up the chain of command. And then it turns out both of my deployments, we have one crash, and still nothing happens. But it's just no way for the little guy to voice their concern.
No, I mean, it's a fair point. And so you've got, and I'm somewhat familiar with the MV22 or CV22, which is our version of it, the Osprey. I had a project many years ago funding a particulate sensor for the inlet of the Rolls-Royce engines. So we could start to measure the mass particle ingestion to the wear and tear of the engine. And it was a good effort and it worked. We mounted them on test engine at Rolls-Royce in Indianapolis. It worked. We did small lab tests and it measured it properly. Everything worked, but it was never integrated into the bird. Why? I will tell you the reason why, but I can't because this is being recorded. But it got into politics and money. And so I'll leave it at that. That bird is a very maintenance prone aircraft, but it flies fast, right? A Chinook is doing, I don't know what the speed of a Chinook, CH-47, maybe 130 miles an hour. And I could be wrong, but I believe it's in that range. And a CV-22 is probably doing about double that. And so the speed, the target, time to target, those sorts of things are, diminished, shortened dramatically, which is good for mission effectiveness. So, but yeah, no, I understand your point there. And there's been a variety of aircraft that have been problematic over the years. The Harrier for the Marines was a very problematic aircraft as well. It's part of the reason why I believe the UK stopped using it, because it's kind of maintenance prone, a little bit dangerous.
Thank you very much.
But these are just my thoughts. Do not represent the governments nor the command, okay?
Good to go.
Gotcha. Any other questions? Last slide. So I'm not sure how many people have seen this, and I know we don't have much time, but I'll quickly go through it. This is basically, it was developed by NASA many years ago, and it's the S curve of technology development. Bottom axis is measure of applied effort. That can be resources, people, labor hours, money. It's usually all linear, somewhat linear there. And then the vertical axis is measure of advancement. How much more capability are you experiencing? And so, as I mentioned before, at SOCOM, we don't have a whole lot of money. And so where we try to pick up on is right here where that star is. And that is, let the DARPAs of the world, the big Navy, ONR, Office of Naval Research, Naval Research Lab, and those places, Department of Energy, spend their dollars to start to make something more capable, a basic technology. And then we'll pick it up and try to make it into a warfighting capability, put some more effort into it so that it can be fielded. But with time, it diminishes. You're just like all systems, just like all your iPhone, from your iPhone 2 to your iPhone, whatever they are now, capabilities continually improve. And so what is the next improvement? What will cause you or the capability to improve? And sometimes it's not just better of the same thing. Sometimes it's something very additional. So for example, dry combat submersible. One of the critical limitations of that vessel is power management. And if we could come up with, or a power management or power system come up with, say, doubles the energy density, that would make that craft so much more capable. And you would then hop off of one development curve, if you are a capability curve, onto another and bring it to the next level. So things have a finite, advantage, technology advantage. Heck, look at the cars we drive from the 50s to now. It's not even close to the same thing. So it's a way of visually looking at the investment curve and the time. And you can't keep polishing the rock on the plateau. Says to the guy that invented the horse buggy whip. What he missed was that the horses were no longer be relevant when the production of the car went into mass production. And so he could have made the finest buggy and buggy whip, but at the end he was overtaken by a different technology. And so you always have to be thinking in those terms and not be beholden to one thought or way of doing things. So any questions? Anybody still awake?
Just a little bit.
Yeah.
Yeah, good, good, good. I am.
Okay. So any last questions for Mr. Martin before we wrap up?
No, I think you covered just about everything.
Okay.
Okay.
Then I
So,
will
Well,
stop.
my parting shots is make a difference. Make a difference in our world, okay?
We'll do our best.
Yep, please do. I
We'll even
need you
try to make
to.
it a good one.
Yep, I need you to.
Thank you so much for this. It was really helpful.
Thank you for your time.
Thank you for yours.
Okay. So with that, I'm gonna stop recording.